Hi, welcome to the Calculus 3 lecture series. And we are in the unit Vector Calculus. This is our lecture number 4 here. For the previous lecture number 3, we introduced the vector field. And so for this lecture, we're going to talk about the line integrals here. And for the lecture number 4, I'm going to divide it into two videos. The first video we're going to talk about is how to do the line integrals over the scalar field. And then the second video, we're going to talk about how to do the line integrals over the vector field, okay? So let's go to our lecture notes and let's get started here. Okay, so now here's like I mentioned before, for this lecture, I'm going to divide into two videos. So the first video, we're going to talk about the line integrals over, we call this a scalar field. Okay, then we're also going to talk about, in the next video, we're going to talk about the line integral over the vector fields here. Okay, and so the scalar field is just like our typical, like R2, R3 coordinates, right? Okay, so besides we know the formula, we want to know what is the meaning of the line integrals over the scalar field, okay? So the first is, let's take a look here, and back to the, calculus 2, the first time we experience the line integral is when we try to find the arc length for curves here, right? Okay, so like, so here, let me get my, so like in the Calc 2 here, we talk about the arc length. So for any given curves here in the R2 space, then if I want to find the length of these curves here, okay, so when we try to find the length of the curve, okay, so let's start with the first topic we're going to cover in this videos here. So what is the line integral over the scalar field? Okay, so let's take a look, when we are in the Calc 2, right, the Calculus 2, so for given, like, so for given curves here, right, so this is y equal to the f of x functions, and then I want to find, for example, this is my A, this is my B here, right? So the first thing we say, okay, how about if I want to find the length of these curves here? So we say, okay, if you want to find the length of these curves here, so what do we try to do? So, the formulas here, we say the length of the curve will be what? We say will be A over B, then we say this is the 1 plus what? dy dx to the squares, right? And then times the dx here. Or, the same ways here. So like, if you change this one into the parametric form, so we say if x is equal to some function of the xt and the y is equal to some of the yt's here, and then, you can do the same way. So the length of the curves here, right? So we will say it will be equal to the A star to the B star. So where this is a T is from the A star to the B star, right? So we say if you want to change it to parametric form, it will be the same. Now instead of using the 1 plus dy over dx squared dx, so we say, hey, you can do like this, is dy over dt square plus dx over dt square, right? So to the dt. That is, how do we do in the calculus 2 here, find the arc length here. Okay, so now in the calc 3s, right? Let's take a look in the calc 3s here. What do we mean here? Okay, so if I have a function z is equal to the f of xy here, and I'm going to find, I'm going to find the line integrals of the f of xy. So what is the, okay, so if this is my x, y, and z, and this is my, okay, so this is the surface area of the xy, right? So this is the surface of the area. This is z equal to the f of xy here. So now if I say I have a curve here, so for example, I have a curve like this, right? So this is my curves here on the xy planes here. And now when I try to do the line integral over this curve, what's that means here? That means, imagine that, right? So like in here, you use kind of like a, so you imagine like this way, you have like a, okay, so like okay, so I don't know, you can see that or not. So it's kind of like you have like a knife, you do a cross sections along this curve here, and then you try to find what? You're trying to find this cross section area. Okay, so you try to find this cross section area of this curve. That's what I graphed in the yellow. That is what is the, the line integrals in the scalar field in the R3 means here. So your curve is here defined by XY in the XY planes, right? So it's similar, or you can have a curve in the R3, doesn't matter here, right? So what do you do here is like, then you you imagine you have a big knife, and then you're cutting through the curve, and then you want to find the cross-section area of this curve. That's why we do that's what we defined as the line integrals here. So how do I do that? So in order to do that, so the height of these cross sections, right? So the height of the cross sections here, right, is your f of x functions here. So by Riemann-Sum concept, right? So I'm still, because it's the area, it's a cross-section area, right? So I'm still using the height times the width, right? But the width here, this is the what? This is the curves here. Okay, so I know I can find, so this is my curves here. So that's why I say I can find that this is D to the S. So for each arc sine, the length of this arc, the small area of the arc, I say is delta SI. So I can treat this is the base, or we treat this is the width of my rectangle, then times whatever the point you touch the function f of xy here. Okay, so that's what is the definitions about the line integral over the scalar fields here. Okay, so now let's take a look at our former definitions here, right? Okay, so we said f is a function of two variables, and the c is a smooth curve of RT is XT plus YT here, right? So this is, we call this is the, what? This is the parametric forms, right? So that means you defined, so here this is the, so here this is your curve defined at XY, right? So that is, we said it's the curves here. So now the T is A between the A and the B here. So the T is vary. So every time you give a T value, and you will get a what? Every time you get a T values here, you will get a XT value and a YT value. So that's how do you define these curves here, okay? So we say, so we use the same Riemann-Sum concept. So we say we divide this into n subintervals. That means this is my curve. I'm trying to integrate over. So in here, that's why we say, okay, I divide this into, right, several right? So I divided these ones into several, like the small intervals here. So that is the delta SI here, right? So here, this is like this one is delta SI, this one is delta SI here, right? So now, just like, we do the Riemann sign, you can choose the left point, the right point, or whatever, the middle point here. So we said, you can choose the TI in each subintervals, and then the TI star will give you a point X, Y stars here, right? So then you plug in the XI, YI star, this will be the height. So the height times the base, height times the width is equal to the area of this rectangle. And now if you go through the whole this line, so the Riemann sign is always is like, I don't have the equal sign here, it's a summation, right? So that means you add all those together, so it will be an approach to infinity. That means if you cut this one to a smaller, 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 and smaller, right? So that is how do we define the line integrals here. Okay, so be very careful about these ones here is ds here, right? So that means I'm cutting this curve into a very small segments. Each segment is the length, right? So the delta S is here. That is the length of this small arc, right? That's the length of this small arc here. And then now, so one way we can do that, so how do I find the length of this small arc here? So let me enlarge it a little bit. So for example, this is my delta S, right? Okay, so this is my del S, right? So the I here, I mean, enlarge one of these things here. So then by the, by the Pythagorean theory, and you see here, this one's here, this is the X coordinates, this is Y coordinates, right? So this is X coordinates. So this will be what? So this is dx dt, and this is what is dy dt, right? Okay. So this is dx dt and dy dt. So I know the ds here is what? ds by the Pythagorean theory, right? So the ds, you can approximate dx, right? So by the Pythagorean theory here, so this is the hypotenuse. So you can approximate this arc length by using the Pythagorean theory. That's why I have a dx squared dt plus dy squared dt. And then you substitute what is your x, what is your y, the t. Now you change this line integral into a what? Into a typical calculus 2 integration, right? So you integrate against what values here? You integrate what is the dt values here, right? So you integrate for the one, the one variables here. So in the same way, if you have x, y, z if the w is equal to the f, y, z, and in the fourth dimensions here, so you can do the same way. You can use the parametric. You change everything to t, so then you take the integration for the dt's here. So from this ways here, now you change everything from the like the 2 or 3 dimensions and the delta, delta S here, you can change that to the parametric with the t. So you change your whole integration into the same like dt's here. Well, if this is still a little confusing, so let's take a look, all right? Okay, so let's take a look at this, how do I do this one? So they said evaluate YDS, and the C's here, right? So this is a DS, and I'm along these curves here. So let's say C is given by xt, t, yt equal to t squared, t cubed. T is from 0 to the fourth roots of the seventh here. So I graphed it for you. Okay, so this is what is the graph. Those light blue one, light green one, this is y equal, so this is the z equal the y surface, right? So then this is the red ones here. This is the curve I'm going to, this is my C's here, right? So this is the curve I'm going to integrate. That means, imagine yourself, right? You use a knife, you're cutting, you're along this curve, you are cutting through that, and then you want to find the cross-section area along these curves here. All right. Okay, so now let's see how do we do it. So this one is pretty straightforward. They already give you the parametric forms, right? Okay, so now I'm going to take a look at the x prime t's, right? So x prime t is what? It's 1. Now what is my y prime t's here? Y prime t is 3t squares, right? And then now I'm going to okay, so I'm trying to find the integration of this line over the y ds. So remember, like a while ago, we said we want to change everything to a single variable. What is this single variables? Here is a t. Then we'll be able to, so we'll be able to integrate by using what we learned in the, the calculus tools here, right? So, okay, so now let's take a look. So first things here, I change it to the t. So it's from the 0 to what? 4th roots of the 7. Okay, so here's a y. So y is a t cube. So these ones here, I say it's a t cube here. And then it's inside here. So it's dy dt plus square plus dx dt, right? So dx dt square is 1 square plus dy dt square is what? This is 3t square to the square, right? So this will be what? This will be dt's here. Now see here, did you change everything to the what the to the format we are familiar with in the calculus tool. We integrate with respect to the t variables, right? So this is the 0 to the 7 to the 4th roots. This is t3. And then this is 1 plus 9t to the 4 dt's, right? And so 90 to the 4 dt. So I can use, I recognize this is what? This will be the u sub, right? So I can say this is 1 plus 94. Then I have a du is equal to what? Okay, so it's so this is 4 times 9 is 36 t what? 3 dt's here, correct? Okay, so 3 dt. So now, because here is only have dt's here, and now I can, okay, so I can do this. Okay, so the u is equal, okay, so 3, so this is a dt here by u sub here, so this is a dt to the key cube. So I need to adjust this ones here, so divided by 36. So I have a du, okay, du divided by 36 equal to the t3 dt's here. Now I can integrate here, this will be the u to the 1/2 and the du, and I have this is 1 over 36 here. I'm going to leave this limit blank right now because after I integrate, I will put it back. So this is 1 over 36. And then here, this is 1/2 plus 1. So it's 3 what? 3/2. And this is u to the 3/2. And now I can, so 3/2, this is the flip is 54, right? 54 u is what here is 1 plus 9 t to the 4th to the 3/2. Now I can put my limit here will be 0 and the 4th roots of the t. So you plug in, so what is the answer here? So it's 511 over 54 here. Okay, so that's how do we do the line integrals here. So, the hardest part for the line integral is how do you find this parametric representative, right? If you find it, then it's pretty simple here. Okay, so now let's take a look at the next things here. So next things here is telling you, so let's say if C is a piecewise smooth, okay, that means you can break the C into several different curves. So like C1 is smooth, right? Then C3 is smooth, C2 is smooth, C4 is smooth. So if you are like if the C is piecewise smooth, you can break it into a different line. Then you integrate C is the same like we did in the calculus 2. You can break into two integrations regions here. All right. Okay, so this is the, like I say, if you have two curves, I can break it. Then here is something very interesting. So they said there are two other line integrals. So you can do the line integration over. So here, take a look here, right? So here, be very careful. This is ds is here, right? So they also tell you there are two other line integral methods can be defined. Okay, so one here is you can integrate y along the c respect to x. Okay, so instead of using the arc length, you can use the delta x's here. All right, so that's why in here they say the c, the f of x dx is here. You can change the xt, yt. Then what do you have here is x prime dt here. That means you integrate in these directions, right? So if this is your curves here, right? So now in here, this is from A to B, right? Then you can divide the x direction. So each one here will be the delta x, okay? So now is the delta x here. So because this is a parametric, so if you change back, so see here, that means you can integrate what? Along the dx. So here, this is along the, the arc length is here. Okay, so you can see, so sometimes the people say f of x dx can be think about like it's kind of like the partial line integrals in the x directions here. So it's not the true length, the arc length is here. So the same way you can do to the y directions, right? So when you do the y direction, that means from here, you do like here, right? So you do the y direction, it's the same thing. So it's dy here. And also, sometimes they said if you have, okay, so sometimes if you divide by, so it's not divided, if you separate, you can use like the pxy dx and the qxy dy in a sum, both of them along the same curves here. So then you can just combine them together. All right, so because they have the same curves here. So one side, the one part you can do the dx and the other part you can do the dy here. Okay, so if you're still a little bit confused, let's take a look at the problem. So then you probably will get a better understanding here. Okay, so now in here, I said, hey, I want to evaluate. So this is my given functions, right? So x minus y, x minus y. I want to evaluate, these ones here. And my curves here is given. So this is a nice often they give us the parametric form of the curves here, right? So I want to evaluate okay, the value of along the x and along the y's here, right? So let's take a look here. Okay, so I have a x prime. Okay, so the first things here, let's take a look at what is my x prime t. X prime t is what? Is ETs, right? And then I can take a look at y prime t. Y prime t is what? Y prime t is negative e to the negative t here, right? Okay, so let's take a look at the x minus y dx here, right? So that means x is what? So this will be 1 plus et minus 1 minus e negative t, right? So what is here is dx. So dx is et dt. And the t is from where? T is from the 0 to 1. So you change a complicated function to a t function here, right? Okay, so now you can combine these ones a little bit. So this is 0, 1, 1, 1 cancel. So you will have et, right? So you have et plus e the negative t times et dt, and then here you have et, so this is e2t plus 1 dt here. Then you substitute, so this is a pretty easy integration. So the answers here, this will be the e2 over 2 plus 1/2. Okay, that means if you integrate this from the x direction. Okay, now let's take a look if I integrate from the y direction. So this is 0, 1. So still inside here, still, okay, it's the same here. So this will be 1 plus et minus 1 minus e the negative t, so this is x minus y, then times 1 plus y prime t, right? So this will be e negative t dt here. So if you combine it, you will get this is 0, 1, 1, 1 cancel again. So you have et plus e the negative t and e the negative t here, dt. So what do you have here? So you have 0, 1, 1, 1 what? 1 plus e to the negative 2t here, right? dt. And then this one's here is a pretty simple integration. And so this will be the 3/2 minus 1 over 2e squares here. Okay, so as you can see here, so you have like when you integrate along the x and integrate along the y, you get a different answers here. Okay, so that's why we said, when you integrate for the dx and the dy, that means you integrate this line. So instead of using the arc lengths, right? So there's really 3 ways you can find the evaluate the line integrals, depends on which way you want. So the arc lengths and go to the x direction and the y directions here. Okay, so now let's take a look at another examples here. So evaluate this is the c, so it's x, y, z here. So in here we know the x, y, z. If I said w is equal to the x, y, z, that means you are looking like the R4 dimension. And then c is a helix with the defined as x equal to t and y equal to the sine t, and z is equal to the cosine t, and t is from 0 to pi here. I did a graph for you and try to show you what is the helix looks like. So this is the graph of the helix here. So you you look at it, it's kind of like the springs, right? So it's kind of like the spring hanging on the space here. So in here, this spring is kind of circling around like the x-axis here, right? So I did like the 2 views, so you'll be able to see what is a helix means, right? So that means right now I'm going to evaluate these line integrals along this. Okay, along these lines here. Okay, so now let's take a look. How do we do it? So it's the same ways here. So let's see here, we said the xt. So x prime t is what? 1. Okay, y prime t is equal to the cosine t, and z prime t is equal to the negative sine t, right? Okay, so now let's just change these integrations. So I can change this line integration to our normal, like the one variable integration. So t is from 0 to pi. So I say 0 to pi x, right? So it's t times sine t times cosine t here, right? And what I have inside here, I have inside is the 1 square plus cosine square t plus negative sine t to the squares, right? Okay, so negative t sine to the square. So cosine square plus cosine square. Wow, that's nice. They are nice to us. This one is simplified to ones here. Okay, so then in here, oops, here. So this is the dt's, right? Okay, so this will be the 0 to pi. So this is a t sine t cosine t. And this is what? This is the square roots of the two dt's here. Okay, so now in here, you can use the double angle formula. So I change a little bit. So this is 0 pi, right? So then this will be the square roots of the 2. Then this is the t sine 2t dt here, right? So here, I just combined these two. So this 2 here is 1/2 sine 2t's, right? Because sine 2t is equal to 2 sine t cosine t. So this is 1/2. So 1/2 and this square root of 2 become the square root of 2 on the bottom, see here. Now you can use integration by parts, right? So now here you have a t and here, so you can do integrate by parts. And now, and you can get the answers here. And so it will be 1/4 times square root of the 2. Then this is 2t cosine 2t and minus sine 2t. And my limits here is from 0 to pi here, right? So my final answer for here, this is the pi, the 2 square roots of the 2 here, okay? And now, okay, so now we're going to stop the first videos at here. So this is the line integral over the scalar field. That means the, it's just in the regular R2, R3, R4, whatever, right? So there's no vector, there's no force acting on that. All right, so then the key things here is that's the formula, the key formula we have is here, right? So you need to change you need to change your line integral by using the parametric, right? So you change x to a parametric form, y to a parametric form, and then you do the dx dt square plus dy dt square. Just very, very similar like we did it in the calculus 2, find the length of the arc, right? Okay, so in here, the few examples here, the problems, they already give you the parametric form. So for the line integrals over the scalar field, the hardest part, if they do not give you, the parametric form for the curve or you try to integrate, then that will be kind of hard to find it. After you find it, then you just basically, you need to change that to the regular calculus 2, one variable integration. And then you just use whatever the tools you learn in the calculus 2 to integrate that. Okay, so now I'm going to stop in here. The next ones here, we're going to take a look. What is the line integral over the vector field? So what's that mean? How do I do that? And what is the, the physical meaning for the line integral over the vector fields here? All right. Okay, so that's it. And I'm going to stop here for this part here. Okay, and I'm going to talk to you next in our next part here. All right. Bye.